This is Unit 5, Lesson 7, titled Percent Yield, and the objective for this lesson is that students will be able to calculate the percent yield of a chemical reaction and use it to evaluate the efficiency of their experimental procedure. The vocab is percent yield, theoretical yield, actual yield, and sources of error. Alright, so something a little different here is I already gave you a reading, so the purpose of this video is to, I guess, summarize and draw out the key points, maybe in a little bit more explanation than from the reading. So here's what I'm going to assume. I am going to assume that you already read this. Alright, so if you didn't, your job is to pause right now and go ahead and read it, because what I'm going to do now is elaborate a little bit and summarize the reading. Okay, so again, pause me if you need to. So in this first paragraph, this highlights the difference between the theoretical yield and the actual yield. Here's what I want you to think of when you hear theoretical yield is the theoretical yield is the value that I should get based on the math and the law of conservation of mass. Right? Like the law of conservation of mass we learned said that if I put in a certain amount of something, then I should get a certain amount of something else out. So mathematically, based on this law, I have to get that amount. Alright, so this I would deem a calculation. Okay, it's a mathematical prediction. The actual yield is different, because the actual yield is when you actually are doing the physical chemical reaction. You are taking chemicals, doing the reaction, and it's not a calculation, it is a measurement. You are actually physically measuring the amount of product or whatever that you have made. Okay? So that's the difference between the theoretical and the actual yield. And if you're confused at all, again, I want you to pause and write down a summary of the difference between those two. Otherwise, I'm going to keep moving on here. So, again, after you read this paragraph, you should have walked away with the fact that the theoretical yield and the actual yield are often different. So what the math says that I should get, I don't really usually actually get. And this paragraph, or these points, highlight why I might not get that value. And the term, this is a vocabulary term, sources of error. We've talked about these before, so I didn't necessarily define it. But if you're confused as to what sources of error are, they are procedural errors that you make that cause inaccurate data. Okay, so sources of error lead to your actual yield not being your theoretical yield. And I wanted to draw an arrow up here. Okay, so sources of error affect your actual yield, which makes your actual yield different from your theoretical yield. All right. I didn't mean to draw that. Okay. I'm going to save you the talking about all of these. I think we did this in class. And these make more sense when they're in context. But certainly ask me if you have a question about any of them. Okay. So we actually want to quantify, and again, sorry, I'm in this last paragraph now. We want to quantify how far off you are from what you should have gotten. Okay? Because if you think about what percent means, hopefully you would tell me that percent means, I'm going to write it down here, part of a whole. And when we say yield, we're talking about a chemical reaction where we're, yielding something, making some amount of product. So if you take a look at the equation, I actually really don't want you to memorize the equation. I would love if the equation made sense to you. So look at this equation. It's the actual yield over the theoretical yield times 100. So look at this. And let's understand how that's a percent. Again, a percent is part of a whole. So what's our whole? It's on the denominator. Our whole is what we should get. Okay, the theoretical yield is what you should get. So if stoichiometry says you should make 10 grams of your product, then you should get 10 grams of your product. That's your whole. Part of your whole, the part goes on the top. So maybe you only get 9 grams, you only measure 9 grams, right? Because you had sources of error. So you measured 9 grams, you should have gotten 10, so there's your part of a whole. This will give you a decimal, right? 2 numbers divided by each other give you a decimal, and that, my friends, is why we must times it by 100% to get a actual percent. That's how you change a decimal into a percent. And that's the math behind it. So you might assume that usually the percent yield is less than 100%, but sometimes it's more than 100%, you'll find when we do our lab. Okay, so again, these are our notes. Please, if you already sort of understood them, then you don't have to listen to me blab about it. But for those of you that maybe missed class, let me explain this. So here's our equation from the last page. And just, what does that actually mean in words? Can you explain to me what that means? And hopefully you would say that it's how far off your measured value, which is your actual yield, is from your calculated value, which is your theoretical yield. So conceptually, that's what that means. Life lesson, don't just memorize equations, stop to think about what they mean. Characteristics of percent error are that they are expected to be more or less than 100% due to sources of error. So when you do your lab and you actually do the reaction, I'm not going to expect that you get 100% yield because it's very common to have sources of error. It's just part of life. Oops. Okay, so I'm going to go over the example again from class. I'm going to zoom in a little bit. Okay, it's twisted. All right, close enough. Okay, so you have your reaction here. We have ammonia reacting with oxygen. It forms nitrogen monoxide and water. And 20 grams of the oxygen gas reacts with ammonia. 20 grams of this reacts with this. If a reaction is carried out in the lab, 11.2 grams of water is produced. So it makes 11.2 grams of that. Calculate the percent yield of the reaction. Okay, so if it asks for percent yield, I immediately think of the equation, which is actual over theoretical times 100. Okay, so if I know the equation, I know I need those two values. So see if you can read through the problem and find the actual yield. You might need to go back to the definition, read the definition again, and see if you can pick out the actual yield. All right, spoiler alert, I'm going to give it away, so pause if you need to. But the actual yield is this. 11.2 grams of water. How did I know that? Well, it talked about a reaction happening in the lab, which means you're actually doing the physical reaction, so that's how I picked out the actual yield. If it talks about some keywords are like lab, experiment, the word actual is a good clue. Those are all context clues that it's the actual yield. So theoretical yield means how much of this water should I have gotten? Okay, I actually got 11.2 grams of water, but I'm wondering how many grams of water I should have gotten. And if you read the problem, it doesn't give you information about how much water you should have produced. It only gives you information about 20 grams of oxygen gas reacting. But I'm not interested in oxygen gas. I am interested in water. So how can I use that 20 grams of oxygen to figure out how many grams of water I should produce? Well, if it's giving me one value within the chemical reaction and asking me for another value, that sounds a lot like stoichiometry. So I'm wondering, how do I get from grams of O2 to grams of H2O? And that little organizational chart we made is coming back to me, and I think that I can use the grams of O2 to find moles of O2. Once I get moles of O2, remember I can use mole to mole ratios to find moles of H2O. And I can always convert moles of one substance into grams of that substance using molar mass. So if I follow this plan, I can get grams of H2O. So let's go ahead and do that, and obviously pause me if you would like to try it yourself. I put grams of O2 on the bottom and moles of O2 on the top. I'm going to go from moles of O2 to moles of, what do I want? Water. And then the last step is to take those moles of water and turn them into grams of water. Again, such a good habit to set up all the units, because see how they all cancel out? Boom, 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 and I'm just left with grams of water, which is what I want. So grams to moles is always molar mass. It's always 1 mole per 16, and 16 is 32. The mole to mole ratio is 6 to 5, right? 6 to 5. Yep, I lined those up correctly. And then grams to moles, we're back to molar mass. 1 mole, and then, of course, I have the molar mass of water memorized. 2 H's, 1 O is 18.02. Okay, so I actually go ahead and I put that in my calculator and I find the answer. And I get 13.5 grams of H2O. So that's what I should have gotten. Oops, I didn't mean to draw that. Okay, so what do I do next? Oh yeah, it wants percent yield. Actual over theoretical, part of a whole, times 100. So I have 11.2 grams of H2O over the 13.5 grams of H2O times 100. And that gets me about 83% yield. One thing to double check is to make sure that these are always the same. A very, very, very common mistake is that people put this number, if you look up here, into that equation. Usually on the bottom, like they would write 11.2 grams of H2O over 20. And it just doesn't make sense. What you're telling me if you do that is that, oh, I thought I was going to make 20 grams of oxygen, but I actually made 11.2 grams of H2O. Right? That doesn't make sense. You don't want to compare oxygen to water. So if you label the unit and the substance whenever you do this, it should be a good clue that you don't put that in there. Right? It would be a big red flag. So always write those down to check yourself. So the last thing that you want to do, although it doesn't ask, but good students would do this, is what does that mean? 83% yield means basically that I got 83% of what I expected to get. I expected to get 13.5 grams, but I only got 11.2, so I only got 83%. So that means I carried out my procedure to an 83% efficiency. So cover up these answers if you have not tried them yet, and try them, please. But if you did try them, here are the answers, and let's just make sure you understand that your hypothesis is based on the math, is based on the law of conservation of mass, so that's your theoretical yield. Okay, here's what I should get. And then part B asks, which is a measurement, which means it's data, right? It's data within your lab. You're going to measure the actual yield. You're going to do your whole reaction and then actually measure the product. You're going to get that. Part C. Oh, if I carried my procedure out to 100% accuracy, then I should get what I expected to get, which is the 20 grams. Okay, but I didn't, so part D asks which one has error. Is it this one or is it this one? And it's always the actual yield. Always the actual yield. Okay, error happens within the lab, and remember that you do your hypothesis before the lab even starts. So that can't be wrong. That's based on math. Okay, never tell me that that has error in it. And then finally it asked, do you think this lab had sources of errors? And my answer is yes, because the actual yield was not equal to the theoretical yield. And you cannot reverse these, meaning don't tell me don't put theoretical here and actual here, because it wouldn't be correct. Okay, if you switch those, it implies that, actually, sorry, let me talk about my answer. The way that I worded it implies this has error, and this is what I should have gotten. If you switch those, you're going to say the opposite, which is this has error, this is what I should have gotten, which isn't true. So I'm going to work through problem number 2. So if you want to try it, pause me. If you're just looking to check your answer, then I might fast forward and see if you got the right answer. And if you didn't, you're just going to have to go back and listen to this whole thing. Okay. So I have this equation here. Oops, I'll do it in red. I have this equation here. And it says if I start with 40 grams of magnesium, which is right here, and excess nitric acid, which means I have as much of the other reactant as I want, how many grams of hydrogen gas will I produce? I'm starting with 1.7 grams of hydrogen. No, I'm not. It says 1.7 grams of hydrogen is actually produced. What's my percent yield? Okay, percent yield. It's asking for percent yield, so I remember that it's part of a whole, actual times theoretical times 100. So I know that I need the actual and the theoretical values. I also know that the actual has to be given to me in the problem because I'm not going to go in the middle of this and run an experiment. And it seems like it's telling me that 1.7 grams of hydrogen, which is always H2, was produced. Actually. The theoretical needs to be some amount of grams of hydrogen that I should have produced. And wouldn't it be so nice if they just gave me that value, but they don't. They give me 40 grams of magnesium, which is just Mg up here. So I think I need to do some stoichiometry to go from grams of magnesium to moles of magnesium to moles of, what do I want to get to? H2. 2 grams of H2. Yay, that fun process. That's my plan of attack. So I gotta do grams of Mg, moles of Mg, moles of Mg, to moles of H2, and then moles of H2 to grams of H2. So cancels, 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 and that's what I want. So now I fill in the numbers. 1 mole, and magnesium, I don't remember the molar mass. I had to look it up. 23.4 grams on the periodic table. Then I'm going up to my chemical equation here. Don't understand why it won't let me erase. No. Sorry this is so messy, but I have to balance this equation. So if you balance it, I'm just going to do it in my head. I believe that for, I think it's 1-to-1. Yep. So that's easy. But you do have to balance the chemical equation there, because see how there's 2 of these, but only 1. I think that we just needed 2 there. Okay. Now the last step, for every 1 mole, it's 2.02 grams. So go ahead and put that in your calculator and see what you get. And you should have gotten somewhere, if you rounded, to 3.5 grams of H2. Okay, so that's how much I should have made. So I put that up here. And and then I'm going to times it by 100. It's always a good idea to sort of have a range of answers, and it looks like that's pretty close to half. I think I got about half. Let me put in my calculator. And I get 49% as my final answer. So again, I take a second to think about what this means, and it means that I got about half of what I expected to get. That's kind of lousy. I mean, 50% is pretty low. You should have gotten 3.5. You actually got 1.7. You lost half the product, or you didn't make half the product. So your efficiency was pretty low for this experiment. So after this lesson, make sure that you're able to do these following things. Explain the difference between the theoretical yield and the actual yield, and why they are usually different, and hopefully you discuss sources of error in that answer. Make sure that you are able to explain how to calculate percent yield, which would look like explaining the equation. And then 3, can you pick the actual yield value from a problem? And then can you calculate the theoretical yield using mass-to-mass stoichiometry? Sometimes students can't differentiate between these two. They don't know the actual yield from the theoretical yield, so you need to make sure you do. And then finally, can you calculate percent yield and evaluate how efficiently the experiment was performed from that value? So can you find that 83% yield or whatever it is, and then explain to me, sort of make a judgment call on how efficient they were in their experiment. And hopefully if they got like 10% yield, you would tell me that they were pretty low efficiency, whereas 90% yield is pretty high efficiency.